42, compare the amounts of energy in neutral atoms and in the crystal lattice structure. Well, again, when these atoms bond, they're trying to get to a lower energy state, and a lot of foreshadowing here. They actually would like to be more random, but they want to get to a lower energy state, more stable. They give off that excess energy. So they're going to minimum potential energy or lower potential energy than they were when they were individual non-bonded atoms. Test question number 13, which is hint number 43. Describe the properties of ionic compounds. I think this was the first thing in the notes in this particular section, so you have a nice little chart and summary there. I have a drawing there for you showing a crystal lattice. We also go back to the Bonds video lab, the first one we did in this chapter, where you compared ionically bonded substances to covalently bonded substances by melting them and dissolving them in water. And think about some of those properties. Our ionic substances were the ones that we didn't see melt when we put them on the hot plates over in the lab area. Our hot plates didn't get hot enough to melt an ionically bonded substance, because in an ionically bonded compounds, we have bonds in between all of these ions in every direction, and that takes a lot of energy to break. So they have high melting points, and because of that, they're also going to have high boiling points. Ionic substances tend to dissolve in water. Not all of them, but the majority of them dissolve in water because water attracts those ions and can break apart the lattice structure. They're brittle. Imagine if this was a real salt crystal and we hit this with a hammer. You probably can envision this pretty easily. If we hit it with a hammer, it's just going to shatter. It's actually going to shatter into smaller crystals of the same shape. Because when we hit this with a hammer, we're sliding the ions over a little bit and sort of getting the negatives to line up with each other and the positives to line up with each other, at least a little bit. And when those like charges get close to each other, then they'll break apart. But they'll break apart in planes and end up in the same shape as the original crystal. I do want to make note of that because that's something I'm going to have you draw for me on your honors page that goes with this chapter. So make sure you can really draw and describe what would happen if we hit an ionic crystalline solid with a hammer and jarred those layers over so that the like charges lined up, and then the planes of the crystal, the atoms would start to repel, the ions would repel, and it would break apart into smaller crystals. Excuse me a moment. I have another example of a crystal, which I'll try to hold it in front of my shirt here because I don't think you're going to see it against the white board. This is a calcite crystal, calcium chloride instead of sodium chloride. And you'll notice that the planes are a little bit different here. This is at an angle. But if we hit this with a hammer, it's going to break off in planes and make smaller crystals of this same shape. Again, because of that nice orderly packing of the oppositely charged ions that alternate back and forth. Okay, moving on to test hint number 44. So it's test question number 14. Again, comparing the properties of ionic compounds to molecular or covalent. Test hint number 45 and 46 are very similar as well. So you should know a little bit about all of the common properties of ionic substances and be able to contrast that with covalent. So even though we haven't focused on the covalent bonding part of this chapter yet, take a look at the beginning notes in the chapter because I do have another list and description of properties of covalently bonded substances. And we were comparing them in the first lab, the Bonds video lab, comparing ionic and covalent, and the conductivity lab. So be able to compare and contrast the properties of ionic and covalently bonded compounds. And you know what? That is something else you should think about and make sure you have a good understanding of when it comes honors page time. So let's take a look at test hint 45. Compare the properties of ionic compounds to molecular again. And this question will be referring to the strength of attraction between particles within the compound and particles of molecules of the compound one to each other. So think in terms of this one, in terms of the strength of attraction. Number 16, question number 16, test hint 46. Explain why ionic and molecular compounds have the properties that they do in general. Again, that relates to the strength of attraction between the particles, between the atoms or ions making up the substance. The electrostatic attraction of ions is very strong. It is stronger than the sharing that happens when atomic orbitals on two different nonmetal atoms overlap to form a molecular orbital to make a covalent bond. Covalent bond done by sharing, ionic bond made by electrostatic attraction. Okay, so think of it in terms of the strength of attraction and the types of atoms that are bonded. Question number 17, which is test hint 47. Describe the number of valence electrons in metals, metalloids, and nonmetals. This should be a slam dunk question. We've actually been talking about this for a couple chapters now. We learned it in our electron configuration chapter a little bit. We talked about it in the periodic table chapter, especially in that lithium, sodium, and potassium in water demonstration. And you should know that our metals over on, generally on the left side of the periodic table, tend to have 1, 2, or 3 valence electrons. Now, that's not the limit. Some of the heavy metals have 4, 5, or even 6. There's one with 6 valence electrons, but it also has a lot of energy levels, so those valence electrons are further away from the nucleus, feeling less attraction. But the most common examples of metals, and certainly more reactive metals, would have 1, 2, or 3 valence electrons. Metalloids, in between, you know, they're on a stair step. The ones that are in the higher on the periodic table, where maybe in the second and third energy level, where the electrons in the valence shell are closer to the nucleus, they have 3 or 4 valence electrons. Some of the bigger ones have 5 valence electrons, but they're also further from the nucleus. And you could consider the one that has 6 as well. So it kind of bridges the gap there. And I guess maybe I'll throw in 6, even though 4 is really the best example of the number of valence electrons for a metalloid. And then nonmetals, of course, would have 5, 6, 7, or 8 valence electrons. And the best examples would be something with, 6, 7, or the noble gases with 8 valence electrons. Okay, so this will be a relative, very general question. Like I said, this should be a slam dunk question.